Hello, this is Dr. Martel, and in this lecture I want to go further in clarifying the concept of logical consequence. And following our author's guidance, I'm going to try and do this by way of truth tables. Specifically, I hope to show you how we can use truth tables to establish that the conclusion of a deductive argument is a logical consequence of its premises. So without further ado, I'm going to and turn to the slideshow. In this course, we're mainly interested in familiarizing ourselves with first-order logic as a way of clarifying the concept of logical consequence and mastering techniques for establishing logical consequence. Chapter 4 goes some ways towards clarifying the concept of logical consequence by offering us a rigorous definition of a related, narrower concept, and that's the concept of a tautological consequence. It also offers us a reliable, though also rather cumbersome technique for establishing tautological consequence, the truth table method. On the way to this clarification of logical consequence, we encounter and attempt to clarify in turn the concepts of logical truth and logical equivalence. Next slide on logical truth. Some statements are true in every logically possible circumstance. Any circumstance that makes sense from a logical point of view, right? So it's a circumstance that, among other things, is like not contradictory. Statements are true in every such circumstance. They're called logical truths. Our authors will also sometimes call them logical necessities, and I think they even use the phrase on occasion, logically necessary truths. These are all different ways of talking about the same thing, right? That which holds true logically, no matter what. Consider, for examples, the following, and I have a number of logical truths there listed. A rose is a rose, A is identical with A, C is in the same column as C. Either P or not P, where capital P stands for any wolf whatsoever. So it's what we call a statement variable. It's rather like a variable in algebra. Those stand for any number whatsoever. A statement variable stands for any well-formed formula whatsoever. And finally, either A is identical with A or D is a cube. All logical truths. So on to the next slide, tautology. The concept of a tautology is related to that of logical truth insofar as the tautologies are a subset of the logical truths. So you can kind of think of the tautologies as being a region, right, within a broader territory. Right, the territory is that of the logical truths. The tautologies are a region within this territory. So every tautology is a logical truth, but it is not the case that every logical truth is a tautology. Tautology guarantees logical truth, but the reverse doesn't hold. And I'll come back to this point shortly. A tautology is a statement that is true in virtue of the meanings of truth functional connectives alone, such as the Boolean connectives. Consider P wedge tilde P. This is an FOO translation of what's called the law of excluded middle. This is a logical truth since it is a tautology. And actually, my language here should probably be more precise. It's technically not a logical truth because it's technically not a statement. It's not a woof. It's instead a schema for statements, right? If you replace the P here, the statement variable, with a statement, you end up with a statement, right? You end up with a well-formed formula. Okay? The point here I'm driving at is that this is a schema for logical truth. Because no matter what statement you substitute for P, okay, you're going to end up with a logical truth, and that's in virtue of the meanings of the connectives involved, the wedge, and I'm going to call it tilde, right, the negation symbol. I explain how this works in English in the rest of the slide. Look, any statement that you get by substituting for P, that's going to be a disjunction, right? because wedge is the main connective. It's a disjunction. By definition, disjunctions are only false when both the disjuncts are false. So when both of the wolves connected are false. But here's how negation works. When what it negates is false, it's true. Okay, and so what this means is that it's impossible for both the disjuncts to be false. Any conditions making one false make the other true, right? And so in virtue of the meanings of the Boolean connectives alone, those truth functional connectives alone, any statement that you get by substituting wolves in for P, any statement that sort of fits this scheme, that's got to be true in every logical possible circumstance. It is, speaking of possibility, it's possible to provide a tabular demonstration that P wedge tilde P is a schema for wolves that are true in every possible, every logically possible circumstance due to Boolean connectives. So this is what I'm not referring to this slide called titled truth tables. Okay, so again, it's possible to provide a tabular demonstration of what I said on the previous slide about P wedge tilde P. Right? Any statement that you get by substituting a wolf for P, that's going to be true in every logically possible circumstance, owing to the meanings of the truth functional connectives involved. we can create a table showing this. To create such a table, create a column to the far right headed by this schema, P wedge tilde P. Then create columns headed by each of the wolves connected. And again, in this case, P stands for any such wolf. In the rows below, list every possible assignment of truth values to the connected wolves. Then, for each of those assignments, determine the truth value of P wedge tilde P. This is the schema that we're interested in. The columns of T's and F's we refer to, the columns to which we refer, in order to ultimately determine the truth value of P wedge tilde P are called reference columns. I have listed values under the tilde in tilde P, the negation symbol, right, in negation P, in order to both assist in determining the value of P wedge tilde P and simulate what you'll have to do in the app called Bool. And Bool is a very helpful app for creating truth tables, as I hope you'll see. Truth values of the whole statement, or statement scheme, I should say, appear under its main connective, wedge. So look, the table shows you there are only two members of the set of assignments of truth values to P, right? P could be true, P could be false. What goes on with the whole statement P wedge tilde P when P is true? Well, tilde P, so the negation of P, that has to be false. But the whole disjunction ends up being true because the other disjunct P is true. Right? And what happens now when P is false? Well, when P is false, one of the disjuncts, namely tilde P, is true. And that's enough to make the whole disjunction true, right? And so P wedge tilde P, that's the schema of logical truths. No matter what wolf you substitute for P, you're going to end up with a statement that's true in every logically possible circumstance, owing to the meanings of wedge and tilde, the negation symbol. So on to the next slide. This is about tautologies versus logical truths, the difference between them. Again, Every tautology is a logical truth, but not every logical truth is a tautology. For example, A is identical with A is a logical truth, but it is not a tautology. We could not appeal to a truth table to demonstrate that it is true in all logically possible circumstances. Since it is an atomic statement, this would be its table, and I show that. It turns out that logical necessity, then, also known as logical truth, sometimes depends on something other than the meaning of truth functional connectives. Sometimes it depends on the meaning of predicates, such as identity, right? Or is identical with. By definition, is identical with is a reflexive relation, and hence A is identical with A is logically true. Let me turn then to logical equivalence. As you already know from what you've read about negation and De Morgan's laws, some statements are logically equivalent to others. From a logical point of view, they're just different ways of saying the same thing. They are logically equivalent insofar as they have the same truth values under the same conditions. In other words, any conditions that make one true make the other true, and any conditions that make one false make the other false. So here are some logically equivalent statements. I have a couple of examples. It is not the case that it is not the case that either P or P. And that's one, and that's logically equivalent to not P and not P. Right. Another one, case of equivalent statements. B is identical with A, and B is a cube. Okay. That's equivalent to B is identical with A, and A is a cube. Yes. Okay. So we can begin to clarify this notion of logical equivalence through rigorous definition of a related but narrow concept. As you might expect, that's the concept of tautological equivalence. As with the notion of tautology, tautological equivalence has to do with truth functional connectives. Tautologically equivalent statements take the same truth values for all assignments of truth values to their atomic components in virtue of the meanings of truth functional connectives. Thus, tautological equivalence can be demonstrated in tabular form. So, see the next slide on this. Right, and this slide has to do with a notion called commutativity. That's a notion which pertains to both disjunctions and conjunctions. I demonstrated with a disjunction here. A truth table can be used to demonstrate that either A is a cube or A is a tetrahedron is tautologically equivalent to either A is a tetrahedron or A is a cube. To demonstrate tautological equivalence, I construct a truth table with 4 rows of possible assignments of truth values to the atomic statements, cube A and tet A. In general, the number of rows of possible assignments is 2 to the n, where n is the number of atomic statements, or statement variables like P and Q that stand for any statement whatsoever. Here we have 2 atomic statements. Again, they are A is a cube and A is a tetrahedron. And 2 to the second is 4, last time I checked. And so there are 4 rows, each of which lists a possible assignment. Okay. So again, I've got the statements that I'm interested in, these 2 disjunctions off to the right. And then to the left, I've got reference columns under their common, under their atomic components. Right? These reference columns list every possibility where assignments of truth values to those atomic components are concerned. Okay, we're going to refer to these possible assignments of truth values in order to figure out the truth value that the whole statement that we're interested in takes under those conditions. So if you look at the table, what you can see, as you would expect at this point, is that both disjunctions are true when either one or both of their disjuncts is true. And both are such that they're only false when both of the disjuncts are false. Okay. Another way of putting it, every assignment that makes of truth values to their components, to their atomic components, every assignment that makes one true makes the other true, and every assignment that makes one false makes the other false. Okay. So now to the slide on tautological equivalence compared with logical equivalence. Every tautological equivalence is a case of logical equivalence, but there are some cases of logical equivalence that cannot be demonstrated by way of a truth table. Some such cases are those in which logical equivalence depends upon the meaning of predicates. Case in point would be B is identical with A, and B is a cube. That's one. And B is identical with A, and A is a cube, the other. These statements are in fact logically equivalent, owing to the indiscernibility of identicals, a principle that holds for statements formed by is identical with in virtue of its meaning, and at least when identity statements appear in what I call the extensional context in an earlier lecture. So right, at least when we're not talking about what someone believes or what someone knows or what something is called. Okay, so on to the next slide, logical consequence. One statement is a logical consequence of some others, if and only if there is no logically possible circumstance on which that statement is false when the others are true. We can, again, begin to get more precise about this notion by way of a related narrower concept, and that's the concept of a tautological consequence. A statement is a tautological consequence of others, if and only if there is no logically possible circumstance on which it is false and the others are true by virtue of truth functional connectives. Okay, so again, it's the meanings of truth functional connectives that are key to this notion of a tautological consequence. Thus, tautological consequence can be demonstrated by a truth table, showing that there are no rows in which the conclusion is false and the premise is true. Okay, so next slide on an example of tautological consequence. Suppose I want to show that the conjunction of P and Q is a tautological consequence of either P and Q or R and tilde R, so like negation R. In this case, I'll create columns for the premises and the conclusion off to the right and create reference columns for each of the statement variables, P, Q, and R. Given the number of rows of truth values I will need is 2 to the third, since I have here like 3 statement variables. My table will have 8 rows of truth values. So see the next slide for that. Okay, so what I've done here is I've listed in 8 rows all possible assignments of truth values to those statement variables, P, Q, and R. Okay, and if instead of working with statement variables, you're working with like atomic statements, like at A and cube A, and I don't know, like hadron E, right? Same thing would hold. You'd have 3 of them, and so you would need 8 rows, each of which lists one possible way of assigning t's and f's, right, to those to those three. There is a how to put it. There's a reliable technique for filling out reference columns in truth tables, and the program, or I should say, the app Boole, will automatically employ this technique. In English, here's how it works. You take your first column, right, the one that appears to the far left, and you assign the top half of the column T and the bottom half F, right? So if your column has 8 rows, you get 4 T's and then 4 F's, right? You then go to the next column over to the right, if there is one, and you assign the top 4th T's, next 4th F's, next 4th T's, 4th F's. Okay. You then go to the next column to the right, and if there is one, right, top 8th T, next 8th F, and so on. Okay, and basically you keep doing this until you reach the last of your reference columns, where you will just always alternate TF, 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 right? However many times necessary to fill out the column. That method will reliably create reference columns, exhausting possibilities where assignments of truth values to your atomic statements or statement variables are concerned. Okay. So what we're going to do now, right, is use those reference columns to figure out, for our premises and our conclusion, right, what truth values they take for every possible assignment of truth values to the, well, in this case, to the statement variables. Okay. So the conclusion, P and Q, that's only going to be true when both the conjuncts are true, right? And so we can basically we can set aside the reference column under R completely, because that's irrelevant for figuring out the truth value of P and Q. Just concentrate on the reference columns under P and Q. And we know, given the meaning of that connective, right, the A-frame, right, kind of upside down V or wedge, we know, according to its meaning, that the statement it forms, the complex statement it forms, is only true when both the conjuncts are true and it's false otherwise. Okay, well, that means that the conclusion is only going to be true in the first 2 rows, and it's going to be false in every other row, right? Because in every other row, at least one of the conjuncts is false, right? Either P or Q, or both. Okay, next thing, easiest thing to do, is fill out the column for the premise, negation R, or tilde R. Okay, that column is just going to be the opposite of the column under R. So every place that every row in which R gets a T, tilde R gets an F. Every row where R gets an F, tilde R gets a T. Okay, and I've filled out the column under tilde R, that premise, accordingly. Okay. That just leaves the complicated premise, either P and Q or R. Okay. So to help figure out what truth value that takes for every assignment of truth values to P, Q, and R, I have first figured out what truth value one of its disjuncts takes. And this is something that you're always going to want to do when you're filling out a truth table column for a complex statement, a complex statement that's complex owing to truth functional connectives. Okay. Before figuring out the truth value of the whole complex statement, a truth value you should put underneath the main connective. Okay. You'll want to figure out the truth values of its less complex parts. Okay. Indeed, you generally want to start with the least complex part of the complex statement, and then sort of work your way towards the truth values of the more complex parts until you end up with the truth value of the whole statement. So I'm gonna start here with the first disjunct, the left disjunct, and that is P and Q. Okay, so I'm first going to fill out the truth values for it. Of course, I already know what those are because I've already got them listed in the column for the conclusion. Okay, so I'm just going to put those truth values right under the A-frame symbol in either P and Q or R. Okay, and now I'm going to figure out what that whole statement takes, what truth values it takes for every assignment of truth values to its components. To do this, I'm going to look at the truth values under that A-frame symbol, and I'm also going to look at the truth values under R, right? That reference column. I'm going to look at those. So in the first row, P and Q takes a T, R takes a T. So the whole disjunction takes a T. In the second row, the conjunction takes a T, and so again, the disjunction takes a T. In the third row, R takes a T, and so that's enough to make the entire disjunction true, and so it takes a T. In the fourth row, actually both disjuncts are false in that case. Both P and Q and R are false, and so the entire disjunction takes an F. Fifth row, R is true, and that's enough to make the disjunction true. Sixth row rather. Again, both disjuncts are false, and so the disjunction as a whole is false. Seventh row, R is again true, so that makes the whole disjunction true. And then the eighth row, everything is false, and so the whole disjunction here is false. Okay, so that's how I filled out this rather complex table. So this table demonstrates that the conclusion is a logical consequence of the premises. Okay, and here's how. It shows that it's impossible for the premises all to be true and the conclusion false. Okay, for there is no row in which the conclusion is false and all the premises are true. Okay, I mean, look at those rows where the conclusion is false. So those are going to be rows 3 through 8. In 3, one of the premises is false. Tilde R is false. In 4, the disjunction P and Q are R, it's false. In 5, again, tilde R is false. In 6, again, the disjunction, either P and Q or R, is false. In the 7th row, tilde R is again false. And in the 8th row, again, it's the disjunction P and Q or R. That's the one that's false. Looking at this table, there's only one row in which the premises are all true. But in that row, the conclusion is true. Okay? And so what I've shown here is that it's impossible for all the premises of this argument to be true and the conclusion false. It's impossible owing to the meanings of the truth functional connectives involved. Okay? And so this is not just a case of logical consequence. This is a case of tautological consequence. So next slide, continuing with the example. What I do here is more or less, like, again, explain what I just said. When you construct truth tables with an eye towards logical consequence, what you're doing is you're looking for a row, right, where all the premises are true and the conclusion is false. If you can't find such a row, you've got a case of tautological consequence, and so a case of logical consequence. Okay? All tautological consequence is logical consequence. If you can find such a row, okay, the truth table does not establish tautological consequence, and so it does not establish logical consequence either. Okay, final slide. This slide comparing tautological consequence with logical consequence. So I can demonstrate I can demonstrate logical consequence with the truth table. I can use a truth table to show that the conclusion is a tautological consequence of the premises. Okay, every case of tautological consequence is a case of logical consequence. Tautological consequence guarantees logical consequence, but the reverse doesn't hold. Okay, so there are going to be some arguments where, yeah, the conclusion is a logical consequence of the premises. It's a valid argument, but I can't demonstrate this with the truth table. Okay, because the validity in this case does not depend upon the meanings of the truth functional connectives alone. Okay, as I go on to explain the slide, the problem is not just that some arguments involve so many atomic statements or statement variables like P and Q as to make construction of a truth table impractical. Consider, for example, how many rows of T's and F's would be required for an argument with just 6 atomic sentences. It would be 2 to the 6, and that's 64. You'd have 64 rows in your truth table, right? Rather, there are cases in which logical consequence depends upon the meanings of predicates. Here's an example in which the conclusion is on the last numbered line. Okay. So 1, 2, 3, the conclusion is the last numbered line. My premises are A is a tetrahedron, and it is not the case that A is a tetrahedron. My conclusion is A is in the same column as A. Okay. Same column, that's a reflexive relation by definition. Everything is in the same column as itself. And so the conclusion, A is in the same column of A, is a logical truth, though not a tautology. Right? Hence, it is impossible for the premises to both be true and the conclusion false, because the conclusion can't be false. Though this could not be demonstrated by a truth table. Okay? Incidentally, and this is a last point in the slideshow, is there any way the premises could both be true? That is, could tet A and tilde tet A both be true? Okay. Could those both be true? If they couldn't both be true, right, what would this imply about the argument, about whether it's a valid one or not? I will return to this question in the next lecture or the next couple of lectures, and that is all I have for now.